All right, so today's notes, we're going to cover section 6.5, which is solving exponential equations. And this is a quick definition. An exponential equation is an equation where the variable is an exponent. So something like where I see like an x as a power versus something where like x isn't a power. So just kind of showing us the difference. So this would be an exponential equation because the variable right here is an exponent. So there's two types of problems that we're going to cover today. We're going to cover if their bases are the same, and on the back side we'll cover what happens if they don't have the same base. So our property for today, or our kind of major fact, is what I have written down here, is that if two powers with the same base are only equal if their exponents are the same. So what I mean by that is 2 to some power is going to be the same as 2 to the 5th only if their exponents are the same. So in other words, x must be 5 because 2 to the 5th is the same as 2 to the 5th. So again, two powers with the same bases are only equal if their exponents are the same. So if we're solving an equation, so like if we look at the example here, number 1, which you might need to copy into your notes, first thing I notice is the variable x is part of an exponent. So this is an exponential equation. What I notice is the base on the left is a 4, and the base on the right side of the equal is also a 4. So if we're solving that, they just want to make sure, so step number 1 is just making sure that the bases are the same. But then what we know then, if the bases are the same, their exponents must be equal. So our second step is just to take the exponents and write a new equation, setting them equal, and then we just need to solve for that exponent. So here, x would be equal to 6. So in other words, if I substituted that back in to check, over here we'll check 4 to the 6 plus 3, is that equal to 4 to the 9th? And of course 4 to the 9th is equal to 4 to the 9th. So let's do a few more. So I look at number 2. The first thing I notice is that that variable is part of the exponent. So then I look and see that the base on the left side is 8 and the base on the right side is also 8. So if that's true, then their exponents must be the same. The only way 8 to a power is going to equal 8 to another power is if those powers are the same. So we take the powers, 3x minus 4, and set it equal to the other one, 2x plus 1. And then we just solve for x, and we may need to, go back to our linear solving skills, but if I wanted to get x alone, like I can, let's add 4 to both sides. So we get 3x is equal to 2x plus 5, and then we subtract x's from both sides, so we get x is equal to 5. And substituting, right, 3 times 5 is 15. 15 minus 4 is 11, so this would be 8 to the 11th. And over here, if I did 2 times 5, that's 10, plus 1 is also 11. So we're checking to make sure it works. Now over here, again, I notice that the variable is part of the exponent, and I also do notice that the bases on the left and the right are the same. So in this case, I might just need to remind myself that the exponent here is a 1. So if the bases are the same, I take the exponents and set them equal. So 1, here we'd say 1 must be the same thing as 3x minus 2. So in other words, 3 would be equal to 3x. So if I divide by 3, the only thing that makes this true is x equals 1. So our last example, if they are the same, again, we go a little bit faster. If I notice that these bases are the same, I would take their exponents and set them equal. So 2x must be the same thing as 6, in which case x must be 3. So those are pretty straightforward. Again, that's solving an exponential equation if their bases are the same. What's a little more complicated, though, is solving if their bases aren't the same. So let's just look at number 5 for a moment. I notice that the variables are in the exponents. So this is an exponential equation. But on the left side, there's a 4, and on the right side, there's a 2. So what we need to do first is we need to rewrite one or both of the original bases in terms of a different base that's common. So I have a few things here. Like for example, what I need to do is I need to rewrite the 4. And here's where this first tip comes in. I can't call that a 4, but I could use a base of 2 to represent that. What my tip says is when you're rewriting something, just make sure to use a lot of parentheses. So I'm just going to rewrite the 4. That 4 should get the power of x. So again, I'm just rewriting the 4 on the inside. The exponent on the outside is still the same. Well, instead of 4, I can call that 2 to the 2nd power, just recopying the right side. Now, what's important to note here, as I set up here, is a lot of times we have to use properties of exponents to simplify this before we solve. So here, if I see a power to a power, I know I would multiply those exponents. So after I get the bases to be the same, now I can see that I have common bases. This is a 2, and that's a 2. So I know that from before, if the bases are the same, the exponents must be equal. So after I get the bases the same, now I can set the exponents equal to each other, and then I can just solve for x. So I can subtract x. So I get x is equal to -3. And we can check that work, and I'm going to check it over on the margin here. So if x was -3, is 4 to the -3rd power the same thing as 2 to the -3 minus 3? So here we'd flip it, 1 over 4 to the -3rd. Is that the same thing? And here we can just rewrite this as 2 to the -6. Is that the same thing as 1 over 2 to the 6th? Well, I know that 4 to the 3rd, right? 4 times 4 times 4 is 64. And then 2 to the 6th, so 2 times 2 times 2 times 2 times 2 times 2 more is also 64. So I can see that that value of x made the left side equal the right side. So let's go through a few more of them. So like here, I notice the variable's an exponent, but this base of 5 is not the same as this base of 125. So I need to rewrite one of them. What I see here is I could rewrite 125 as 5 to the 3rd power. And then I would just rewrite 5 to the x. So now if their bases are the same, right, if this base is the same as that base, I can set their exponents equal to each other. And that's already solved. So let's keep going with number 27 now, or sorry, number 7, excuse me. This is an example where we might need to rewrite both of the bases. Here I see a 9, and then the other base I see is a 27. Now, I can't write 27 as a power of 9, right? 9, 81, so on and so forth. And I can't write 9 as a power of 27. So we'll need to rewrite both of them. So instead of 9, I'm going to call this 3 squared. And again, I'm putting those extra parentheses so I can see that I just rewrote the base of 9. It's still getting the same exponent of x plus 2. And over on the right side, I'm just going to rewrite the 27. So it should still get that exponent originally of x. So instead of 27, I'm going to call that 3 to the 3rd power. So as we mentioned before, now we can use our properties of exponents. So if I multiply, here just watch out when we multiply 2 times x plus 2, we do have to use the distributive property. So here, the base is 3, and I would get 2x plus 4. And over here, if I multiply the power to a power, I get 3 to the 3x. And now that they have the same base, right, this is a 4, and this is, sorry, excuse me, this is a 3, and this is a 3, now I can set their exponents to be the same. So I'll subtract 2 x's, so I get 4 is equal to x. And just as a quick check, we're saying is 9 to the 6th power, right, 4 plus 2, the same thing as 27 to the 4th. And here, like, it would be okay to go onto your calculator and just type in 9 to the 6th power, which is a pretty big number, and then type in 27 to the 4th power, and we realize that those are the same ones. So we can always check our work. Moving on to number 8. I see different bases. I see a 4 and a 256. But what I do know is just from my facts that 256 is the same thing as 4 to the 4th. So if I had 4 to the x was equal to 4 to the 4th, if their bases are the same, I can set their exponents to be equal. And that one's nice and easy. Let's move on to this one. Here again, I see different bases. This is a 3, and the other one is a 9. So instead of 9, though, I could call that 3 squared. Now that should get the original exponent of 2x, because all I did was take the number 9 and rewrite it as 3 squared. So on the right side, I'm going to keep that as 3 times to the power of x minus 6. So on the left, I can use my power to a power rule. 2 times 2x is 4x. And I've successfully rewritten the equation, so they now have the same base. So again, if the bases are the same, that must mean their exponents were also the same. So I set them equal to each other. We'll subtract x from both sides. And then we divide by 3, so we get x is equal to -2. So our last one for today, I notice here that we have a 4 and we have an 8. So I can't represent them right now because they're not the same bases. So what base could I use an exponent to get a 4 and an 8? Well, instead of 4, we could call that 2 to the 2nd power, and it should still get its original exponent. And instead of 8, we can call that 2 to the 3rd power, and it should still get its original exponent. So then here we can use our power to a power rule. 2 times 3x is 6x. And on the right, again, when I'm multiplying these two together, I do need to use the distributive property. So we get 2 to the power of 3x plus 3. So now their bases are the same, which means their exponents must be equal. So I write a new equation. We'll isolate the x's, and we'll divide. So we get the answer of x is equal to 1. So that's our method for today, solving exponential equations. Some of them have the same base, and then some of them will have different or unlike bases.